Hello and welcome to Podcast.init, the podcast about Python and the people who make it great. I would like to thank everyone who supports us on Patreon. Your contributions help to make the show sustainable. When you're ready to launch your next project, you'll need somewhere to deploy it, so you should check out Linode at www.podcastinit.com/Linode and get a $20 credit to try out their fast and reliable Linux virtual servers for running your app or experimenting with something that you hear about on the show. You can visit the site at www.podcastinit.com to subscribe to the show, sign up for the newsletter, read the show notes, and get in touch. To help other people find the show, please leave a review on iTunes or Google Play Music, tell your friends and coworkers, and share it on social media. Your host as usual is Tobias Macy, and today I'm interviewing Katie Huff about using Python for nuclear engineering. So Katie, could you please introduce yourself?
Yeah, hi. So I'm Katie Huff, and I'm an assistant professor in the Department of Nuclear Plasma and Radiological Engineering at the University of Illinois. I've been involved in scientific Python for some time now, and I do nuclear engineering research in the context of advanced reactors and fuel cycles.
Can you start by giving an overview of what nuclear engineering is and some of the current research in the field and some of the problem types that you're faced with in the course of your research?
Sure, absolutely. So nuclear engineering is generally the study of nuclear fission and nuclear fusion. These have applications all over the map, both energy, obviously some weapons, there's some plasma applications. So in the context of more fusion type devices, there's applications related to plasma energy. And with plasmas, you can do a lot of things that are not just energy production, including etching materials or many other things. That's not my area, but nuclear engineering sort of broadly includes all of these things. My focus is on nuclear energy, which constitutes about 20% of the energy in the United States, and it's the vast majority of our carbon-free energy in the United States. So, it's something we really rely on, especially now and into the future as we hope to change a little bit of our carbon profile. So it's really important. I think it's essential. Right now, the nuclear energy industry itself uses light water reactors. They're great. They've been safe for a really long time. And there are about 100 of them in the United States. And there are a lot of questions around new reactor designs. Lots of people are studying very innovative designs. But, a lot of people are also just studying slight changes to our current, very well-performing light water reactors. My work is related to some of those more innovative reactor designs and specifically modeling and simulation of unique geometries, unique materials, unique nuclear physics that happen within innovative reactor designs that might have good features. So I'm interested in reactor designs that are maybe better at fuel utilization, maybe better at sort of passive safety, and maybe easier to control or produce a higher heat differential, which can be used in other applications than just energy. So I'm interested in reactor designs that might innovate on our current fleet. And I'm also very interested in the dynamics of reprocessing and recycling used nuclear fuel and what kinds of technological challenges there are facing a recycling strategy for our current nuclear fuel and potential future nuclear fuel.
Yeah, there are a few things that I've already planned on digging into further on in the show, but a couple things coming out of that I'd like to explore a bit more is, in particular, one being the idea of alternative nuclear fuels, because most people who think of nuclear energy are familiar with enriched uranium and the plutonium byproduct that has become so problematic in the global geopolitical atmosphere because of the fact that it's potentially weapons grade. And then also, particularly within the United States, the light water reactors, a number of them are aging out of their expected lifespan, but a number of them have been given extensions to the amount of time that they're allowed to run, which raises some potential safety concerns. So I'm wondering if you can just explore a bit of that to maybe fix some of public perception there, or also explain some of the ideas for future alternative fuel sources.
Yeah, so there's a lot to unpack there. So I'm going to start with sort of this concern that plutonium is so problematic on the world stage. And, I will just sort of push back against that and say that actually, most plutonium, almost all plutonium produced for nuclear energy is fully accounted for. And actually, the plutonium that's caused problems sort of from a weapons perspective was always intended to be made for weapons. So, to my knowledge, there's no significant history at all of nuclear energy sources being, in particular, uranium-fueled reactors and their plutonium byproducts being unintentionally diverted to weapons, if and only if an institution like a government is pursuing nuclear weapons, are those reactors used for this? So, it's actually very rare that it's unintentionally diverted. I don't have any examples of that at all. The vast majority of plutonium for weapons use has been created specifically for those weapons and usually in customized reactors to maximize plutonium production. So actually, having reactors that produce plutonium isn't so dangerous because the fuel form itself, you can't walk away with it, right? So it's quite dangerous. You can't hold it in your hand, so stealing it isn't a thing. And so it doesn't happen. However, if you reprocess that fuel, you can separate out the plutonium, which itself is easy to hold in your hand. But in all of the cases in which we reprocess fuel, it falls into one of two categories. One, the fuel was always intended for specifically the production of plutonium for weapons, and that production is targeted at weapons, and is typically not nuclear energy, like power reactors that are involved in that. The alternative is that, like in France, for example, they've reprocessed nuclear fuel for many decades and separated plutonium, and by simply counting effectively the kilograms of plutonium that are produced in this way, they're able to not lose it and keep track of it. So it's all accounted for. Something else that you mentioned, actually, so addressing these, I like these questions because they are able to allow me to address some of the sort of common misconceptions. So there's this concern that current reactors are aging out of their expected lifespan. And I love the way you said that because it's quite accurate. They are aging out of their expected lifespan. The lifespan, which is 60 years, the license is 60 years for a nuclear reactor. That lifespan was determined well before we understood how long they could run. It was a very arbitrary choice to say reactors can be licensed for 60 years. There was no safety basis there was no significant safety basis for that 60 years because we had no running and operating experience with reactors when we set that limit. And so actually lifetime extensions are entirely based on the appropriateness of relicensing them for safety. And so relicensing actually is going really smoothly for most reactors. These license extensions are going extremely smoothly because reactors in the United States are exceptionally safe and they're kept in pristine condition. They are constantly being updated during regular shutdowns to make sure that any parts that might be aging are being replaced. The one part that they can't really replace is the pressure vessel. But those are holding up really, really well, significantly better than we could have possibly guessed. And right now, I think there's a really strong future for license extensions upon license extensions and the continued safe performance of those reactors. So I don't think that there are any safety concerns with license extensions in the United States, which is just a really interesting sort of public perception issue, actually. Because of the over-concern and regulatory oversight of our industry, I think the public perception problem stems from the fact that there's this perception that if a license ends, that it's expected that the reactor is too old. But in fact, we have no reason to believe that they can't continue to operate safely. And in fact, we have many reasons to believe they will. However, I personally am interested in advanced reactors. I don't think you have to pit one against another. Actually, I think, so to your point about alternative fuels like thorium, for example, which is sort of what you're getting at, thorium does produce less plutonium, and generally speaking, has effectively the same reactor performance as a uranium-fueled reactor. There are a few minor differences, and in particular, some reactor designs, like liquid-fueled reactors, can be either uranium or thorium-fueled, and you can get a lot better fuel utilization out of a molten salt reactor. Historically, thorium reactors are envisioned as molten salt reactors, and so that's why there's this public association with fuel utilization in thorium, but it's actually a little false because you can use a uranium-based salt just as well as you can use a thorium-based salt. So that's an interesting public perception issue. Also, the fuel utilization in thorium reactor isn't actually that much better than a uranium reactor if you're comparing salt to salt, for example. But what I will say is, it is nice to say that it's not producing much plutonium. And generally speaking, things like salt reactors, which we've historically tested in a thorium setting, are really safe. So they have this passive safety that you get from the thermal expansion of the salt during temperature transients, so temperature excursions. Like when the reaction goes supercritical, the salt heats up, the heat has a negative feedback, and it causes the reaction to slow down. So that's great. Oh, you had a great comment, actually. So you were sort of saying, like, what's the hope and direction of the research in this area? And I would say, actually, my hope and direction for research in this area is that in addition to our current light water reactors, we also produce more light water reactors to replace all of our baseload coal energy, which is killing 170,000 people per terawatt hour. For comparison, nuclear kills about maybe 90 people per terawatt hour, and that includes Fukushima and everything. And Fukushima didn't really kill that many people from nuclear radiation, so it didn't actually kill anyone from nuclear radiation. It killed people from stress, is the estimate from the WHO. But generally speaking, I would love to see, in addition to our current light water reactor fleet, we should build more light water reactors to replace coal, and we should build more unique reactors, advanced reactors with more passive safety, in addition to that, to also replace coal. Because we have a lot of coal to replace. In the United States, it's a huge amount of our energy. In China, it's so much worse. So that's my hope, is that we can use all of the tools in our tool belt.
And going a little bit further afield, in terms of the availability of the fuel sources of uranium versus thorium as far as raw materials, is there a difference in terms of the estimated availability of those fuels that would push us towards one versus the other in terms of the designs of new reactors or the selection of fuel sources for them?
Yeah, so the uranium typically has to be enriched, and you can avoid some of that with thorium, but they both have almost infinite resources. And so there have been a number of studies on how much uranium is in the world and how much thorium is in the world. Thorium appears in lots of places, and there are a number of countries with significant thorium deposits. With uranium, the uranium deposits are a little bit more concentrated in certain nations: Canada, Australia, Kazakhstan. There's a few specific nations that have significant uranium deposits, whereas thorium can typically be found in basically any country. And there are very large thorium deposits in India, for example. But generally speaking, the availability is comparable because it's effectively infinite for both. We will not use all that we have, especially at this rate. And there's a ton in the ocean. So something very interesting is that if we do use up all of the uranium that we are capable of easily mining, then there's actually a huge resource of uranium in the ocean. And the Japanese in particular, but also Americans, are looking into economic ways of extracting uranium from the ocean, which has a great sustainability factor too, because it's a very passive, low environmental impact way of mining uranium.
And going back to what you were saying, too, about the reuse or re-enrichment of spent fuel, that's one of the larger policy and logistics issues that is brought up when talking about light water reactors in particular, is what to do with the spent fuel rods, where a number of facilities are currently just storing those rods on site in the hope that eventually we'll have a more concrete plan of dealing with them. In the United States, I know that there was a plan to have them all shipped to a facility that was going to be built at Yucca Mountain, which to my understanding has been put on sort of indefinite hold. So I'm wondering, what are some of the methods that are being researched to address this problem?
Okay, so having to store spent fuel is not unique to light water reactors. And even if you reprocess, there is still some spent fuel to deal with, and it must go into ultimate disposal. It's not a huge problem, and I just want to point out the magnitudes of waste, even if you compare us to solar, for example, that, if you talk in volumes, it's just astronomically larger for solar. It's astronomically larger for coal, but we don't see the waste because it literally just goes straight into the air with coal. All right, so with that out of the way, what I will say is that things are changing a little bit with Yucca Mountain. The most recent change in the Secretary of Energy has meant that there is $120 million infusion of money into the Yucca Mountain project. The license application was under a great deal of back and forth between the Department of Energy and the NRC and whatnot, not because it was technically invalid. In fact, the NRC's report says the Yucca Mountain would be a safe place and that the license application is effectively approved. But the Department of Energy under the Obama administration chose not to complete the license application process. And so what's basically happening at the government level right now is that the license application will be completed so that we do have a operating license for Yucca Mountain. That aside, it's politically infeasible because, the state of Nevada has made very clear that they do not want to store the waste at Yucca Mountain. So right now, the location of that waste is, as you say, on cooling pads at the reactor sites. And all of that has been paid for by 1 mil per kilowatt hour by the utilities. The cooling pads are continuing to be paid by the utilities rather than the government, even though the government was supposed to take possession of the nuclear fuel in 1998. So you have a situation where the government has really reneged on its responsibility to take that fuel, and that's a policy issue that's beyond sort of technical scope because it's really a technically solved problem. There are many safe ways to store this fuel. All that said, I am interested in recycling the fuel for a number of reasons. One, fuel utilization. I care a lot about reducing the amount of mining and enrichment that we have to do. Two, I think generally speaking, reprocessing allows for slightly shorter timescales on which we need to be responsible for the fuel. We're still talking about thousands of years, but it's not tens of thousands of years. And that's great, and we should probably reprocess just because we don't know what will be happening in the world a really long time from now. But generally speaking, you still end up with some fuel that needs to be buried. France has been reprocessing their nuclear fuel for a long time, and they have a much smaller volume and, not toxicity exactly, they have a much smaller volume of nuclear spent fuel. What else is happening internationally? I guess the Swedish have a repository concept. There are a whole lot of nations that are looking toward just directly burying their fuel, and there are some that are interested in France's success in reprocessing. Korea, for example, is very interested in reprocessing spent fuel to use in sodium-cooled fast reactors. But yeah, there's a lot of hope around the possibility of recycling. In the United States, we don't do that because of the Nuclear Waste Policy Act, which is actually based on this sort of unreasonable fear, like we talked about earlier, of plutonium proliferation.
Shifting topics a bit, in your PyCon keynote, you addressed a lot of the use of open source software in the context of open science. I'm wondering if you can briefly go over the ways in which the open source software movement has affected the scientific research community and the ways that research is performed.
So, open science is really important in all science, just by nature of science needing to be transparent and peer reviewable. I feel this way, and many people in nuclear feel this way. A lot of work in nuclear is performed computationally for obvious reasons. It's a complex process that requires really detailed a priori models. And experiments can be expensive and difficult. So we try to validate experiments and do very high fidelity modeling and simulation. And in fact, for this reason, nuclear is responsible for a lot of early computation. There are a number of great projects that are very open. Pine is a good example. It's a sort of data collecting, data interface for nuclear engineering. We effectively make available a lot of the data that you can find online about nuclear probabilities and decay constants and all these kinds of types of data that nuclear engineers really need. We make those available in a single database on your system, and then we give you an API to work with it and do typical nuclear engineering simulation activities on that. You want to create a material and then see what it looks like after some number of years of decay. Pine is capable of doing that for you, and it's got a great Python interface and a great C++ interface. The lead developer on that project right now is Anthony Skopatz, but there's a number of people from the universities, the national labs, all working with this piece of code. Also, actually, the startups in nuclear that are looking at advanced reactor technology. Some of the employees of those startups also contribute to Pine. So that's one good example. It's a great Python package for nuclear engineering, and it tries to be a simple analysis interface for a lot of typical problems in nuclear engineering. Another great example, actually, is the MOOS framework, which is this multi-physics object-oriented simulation environment that was created in the context of nuclear, but is actually extremely useful for lots of scientific fields. And so that's created by the Idaho National Laboratory, and it's an open source finite element modeling framework that uses some very clever PDE solution techniques to make fully coupled solves of very complex geometries possible for basically any partial differential equation matrix. So I use MOOS to do advanced reactor multiphysics. Lots of other people use MOOS to do advanced reactor multiphysics. There's a great set of results out there in the context of nuclear and in MOOS. MOOS is a C++ project, but it's really amazing, and no matter what science you're in, you might be interested in it. One other great project is Cyclist, which is mostly C++, but some Python, and it helps to assess. So I helped to start this project, and there are a whole lot of other people working on it now, and it's effectively an agent-based simulator for the nuclear fuel cycle at a high level. So instead of looking at the very close detail of the multiphysics inside a single reactor, what we're interested in is the long-term, hundreds of years, hundreds of reactors dynamic of our larger nuclear energy enterprise. And so it's sort of like SimCity for the nuclear industry. And that piece of code is also open. And I think what that does for science is in part discoverability, but obviously mostly reproducibility and transparency. When I am doing science, I don't want someone to ever wonder what it was I was trying to do, or if I don't want them to wonder if I've done something wrong and then not be able to check. It's very important for people to be able to look at what I've done in science and be able to check whether it's correct, to be able to double check, that I had the right intentions. I'm always trying my best, so I don't even mind if the code is a little ugly. This small level of embarrassment is tiny in comparison to the importance of transparency in science. And so, I think a lot of people are on board in nuclear for that. So it's a good time in nuclear for open science.
And so going back a bit to nuclear engineering in particular, what are some of the most pressing issues, and what are some of the ways that you're using Python to help with addressing them?
Man, so I think the most pressing issue right now is related to nuclear innovation. So because we have a very strong regulatory body, which is an amazing and important thing, innovation is stifled a little bit. So it's always safety first in nuclear. We are extremely focused on a constant and unperturbable record of safety, especially in the United States nuclear power industry. And so anything new needs to undergo a great deal of review. And so new reactor designs and new ideas about accident-tolerant fuels and new ideas about the way that modeling and simulation might inform our safety case for some of these reactors has to undergo much more review than you would in basically any other industry. The only comparable industry might be the airline industry, actually, which has a similarly heavy-handed regulator, which is good, right? It keeps us safe. But the big problem and sort of challenge is, how do we make innovations happen in nuclear in the face of this sort of universe? Also, nuclear is an extremely expensive endeavor, but is great in the long term. Now, venture capitalists want quick turnaround on their investments. And so how exactly do you fund a nuclear energy startup if that design might take 10 years to perfect and 10 years to license and 30 years after that to build and make a profit? Now the profits will be huge because nuclear actually, makes electricity very cheaply per dollar you put into it over its very long lifetime. But, will that be enough for venture capitalists and the kind of money and effort that's needed to sustain those designs? So that's an interesting thing facing nuclear energy right now, is this kind of difficulty in innovation. But there's a lot of things going on right now. In fact, there's some bipartisan effort on the Hill to make sure that there are laboratory facilities accessible to startups and innovators so that those people can do the kinds of experiments that they need to do in order to back up their safety case for license applications. That initiative is called GAIN, and it's really amazing. And I think these kinds of things are really a hopeful sign for future innovation in nuclear.
And what are some of the applications of Python in the process of exploring the innovations in order to reduce the upfront costs and upfront facility creation necessary to be able to explore those potentials?
Yeah, I mean, I think you put your finger right on it, right? So, like, it's all about exploring. And Python gives you the ability to avoid all the sort of developer effort, right? It really allows the developer to play around, to prototype things. Like having the REPL, really makes Python something that's prototypable. Generally speaking, you can get in there and try stuff really quickly. And generally speaking, that's important for startups. They need to be able to get in, try stuff, and get an idea and like bound the error with some simple calculations before they run any really high fidelity supercomputer style national laboratory multi-physics simulations. And I think that's great. And I think for innovating either at a university or in a startup, that prototyping capability is really important for not wasting scientists' time. And it's really only possible with Python. I think you can have C++ and Fortran on the back end, but a Python front end makes everything so much faster.
And from what I was able to gather reading through the documentation, it seems like Cyclus in particular is one of the interfaces that allows for that rapid prototyping and evaluation because of the fact that it does give you the option of modeling computationally the life cycles of the fuel and the ways that it can be reprocessed or in different contexts and different reactor types without necessarily having to actually go out and physically perform those actions on it.
That's right, and sort of a big system-level analysis can point out the kinds of small sort of technical details that can have a big impact on the world. If you do a big system-level analysis of this or that recycling capability, it's nice if it can take a very short amount of time because that can target, what smaller level details, what kind of fuel utilization you need to look at, what kind of like reprocessing metrics you need to be focused on, because you're able to do much better sensitivity analysis on those smaller level, sort of lower level details of the reactor or the recycling process. So yeah, I think it's really essential to be able to sort of get that big picture pretty quickly and then dive down. And that's what Cyclus is capable of doing, is that big picture.
And what are some of the current or future developments in nuclear engineering that you're most excited about and most looking forward to?
Man, so I think we're really at a precipice. There are something like 40 nuclear reactor startups right now. And, not all of them will succeed, right? In the reality, we'll be very lucky if 3 of them successfully build new machines here in the United States. Now, I do think some of them will be licensed elsewhere. But, I think it's a really exciting time to watch which ones are going to succeed. We've got molten salt reactor designs. We've got other liquid metal fuel designs. There are small modular light water designs. There are small modular but fleetable. I don't know how to describe the NuScale reactor design, but especially interesting modular reactor designs like the NuScale design. There's an enormous myriad sort of set of reactor designs out there, and it's kind of a fascinating race that's really just started in the last 5 years to see whose reactor designs are going to be cheap enough to deploy and like best for the world and easiest to license and like strongest case for the future of nuclear energy. I think we've got a lot of smart people working on it. It's going to look good.
And one of the other areas that nuclear is often seen is in the context of things like submarines or spacecraft, where it's an energy source that's easy to compartmentalize and ship and gives a long operating lifespan without a lot of the logistical and technical issues of other fuel sources. So what are some of the most interesting applications of that you see coming down the road?
Those are 2 great examples, and I think they've been really demonstrated pretty clearly. One really interesting thing that I think about a lot is hybrid energy systems. So right now we're seeing a change in the electric grid such that power generation, because of wind and solar being sort of variable in their delivery, like I love renewables, and I think they're part of the mix. But I want to see how baseload type energy like nuclear power could fit in and enable those renewables. And one way is if you sometimes divert extra energy on the grid produced by your baseload flatline nuclear power, which always produces the same amount of energy no matter what kind of polar vortex is happening. That amount of energy, you should be able to sort of divert some fraction of it to another process. So processes like desalination of water, right? Very important in California, less important in other states, but something very important to keep in mind as an option. Hydrogen production, so with very high heat, high temperature reactors that are sort of on the horizon, we may be able to produce hydrogen with the excess energy from a high heat nuclear reactor. There's high purity steel making can be done with this extra heat. There's a whole fleet of these kinds of hybrid energy system ideas where you co-locate a desalination plant or a hydrogen production plant or a steel production plant at the nuclear reactor in order to help keep the grid stable. And that actually enables renewables to take effect where it might be challenging for them to fit into the grid appropriately otherwise. So I think these hybrid energy systems are a really strong future for nuclear energy.
And I know you mentioned that it's not really in your particular day-to-day work, but fusion is another subject that a lot of people are interested in. And from my understanding, it produces more energy per reaction than fission. And so I'm wondering if there are any new developments in that sphere that you're keeping an eye on.
I'm lucky to be at one of the best fusion energy plasma type departments in the United States. So the department here in Illinois has a very strong plasma fusion group, and they have a fabulous toroidal fusion device called a Stellarator here on campus. It's called Hydra, and they're doing some basic fusion energy research that's going to be really fundamental to the future. And in France, there's a construction project that's getting ready to be complete. It's possibly the most complex reactor ever built, but it's called ITER. And it's an international collaboration towards a toroidal fusion type device. And, I'm really interested to see how it goes. I think the challenges facing fusion right now are 100% in the materials. It can be really hard on the vessel to have one of these very high energy density plasmas inside any containment. And the vessel really suffers in the context of fusion, and it makes the reaction hard to sustain. And in fact, we may still be looking at 50 years until a sustained energy, net positive fusion reaction. So right now, getting sort of net energy positive out of a fusion reaction, despite the better energy per reaction, getting enough reactions to happen on their own can be very difficult in fusion. We just haven't quite harnessed the sun just yet.
And going back briefly to open science, I know that in your talk you mentioned the fact that you're involved with the Journal of Open Source Software as a way to help researchers sort of escape the publish or perish mindset and actually get some recognition for the work that they're doing and the software that they develop. So I'm wondering if you can just give a bit of a background on that effort and some of your hopes for it.
Oh man, yeah, I'm so lucky to be included in JOS, which is a collaborative project among a lot of people. It was mostly started by Arvin Smith, who was previously at GitHub. It's a brand new sort of idea for publishing software. It goes one step beyond the, just assign it a digital object identifier type strategy. And that step is real technical review of the code and the code's capabilities. And I think that's new in the world, and it's enabled by GitHub, and it's enabled by people who, see value, scientific value in research software. And I think it's something to watch. We've gone over 100 publications this year in our very first year, and I think we see, nothing but increase in interest. If you have a piece of research software out there in the world, definitely consider publishing it in its many versions in JOS, because I think it's good both for your own recognition and for the code itself. I think we've definitely seen a lot of code improve, particularly, the usability of build systems and the test suites and stuff in some of this software improve through the review process of JOS. Yeah, so I think it's an amazing thing. I'm thrilled to be part of it, and I really hope to see it succeed.
And are there any other topics that you think we should cover before we start to close out the show?
No, I've really enjoyed this interview. I know I talked a lot about nuclear, so, that's always really fun for me, but, I recognize it may be less for your listeners, so feel free to edit a little bit.
All right. So with that, I'll have you add your preferred contact information to the show notes so anybody who's interested can follow up with you and keep track of the research that you're doing and the developments in the field. Actually, one other thing that I meant to ask is for somebody who does want to find out more about nuclear engineering and keep up to date with the current state of the art, what are some of the best resources for them to look at?
The American Nuclear Society has an institute called the Center for Nuclear Science and Technology Information, CNSTI, and that's where I would direct most people. For information on the nuclear industry, there's something called NEI, and for sort of international policy stuff, I would direct people to the IAEA. All of these acronyms can be Googled pretty quickly if you just add nuclear to them.
Yeah, and I'll add links in the show notes to all of those resources.
Great.
All right. So with that, I'll move us to the picks. And for my picks this week, I just recently finished renovating my kitchen and as such ended up buying a number of different tools in the process. So my pick this week is going to be the Ryobi brand of tools because they're inexpensive while still having a pretty good feature set for somebody who needs to be able to get work done without necessarily investing in full professional grade tools that they're not necessarily going to use in a professional context. And with that, I'll pass it to you. Do you have any picks for us today?
I also have Ryobi in my home. Nice drill set. Yes, so I would like to direct people to this series about nuclear, a book series. It starts with Atomic Awakening, followed by Atomic Accidents, and most recently, just last week, Atomic Adventures. And it's written by this great author, James Meafy, and I have had so much fun reading these books, and I recognize that they're written for someone with a slight scientific bent, but they're definitely digestible by the regular public, and they are so interesting. He really goes through some of the most interesting parts of nuclear energy from a sort of historic and philosophical perspective. The Atomic Accidents book is out of this world fascinating. He goes through basically every criticality accident, primarily in the history of weapons production in the world. And it is fascinating, absolutely fascinating stuff, with lots of good, juicy human details, because that's how accidents happen, it turns out, as humans. So yeah, I strongly recommend this series of books, which are totally digestible by the ordinary public and really, really fun.
All right. Well, I appreciate you taking the time out of your day to tell us all more about nuclear engineering and some of the research that you're involved with and the ways that Python can be leveraged to push the industry forward. So thank you for that, and I hope you enjoy the rest of your day.
Thanks so much for having me. I really appreciate it.